Provable Security for End-to-End Cloud Storage. It will be presented by Matilda Backendal and Miro Haller. Please welcome Matilda and Miro.
All right, thank you for the introduction, Matt. And good morning, everyone, and welcome to this session. As you might have guessed, I'm Matilda, this is Miro, and this talk is going to be based on joint work together with Hannah Davis, Felix Günther, and Kenny Patterson. And in this presentation, we want to share with you a security model for end-to-end encrypted cloud storage and try to convince you that you should use it. But before we get started on that, let's back up the band. So 2 years ago at RWC 2023 in Tokyo, Miro and I presented our takeaways from analyzing the end-to-end encrypted cloud storage provider Mega. And as you might recall from that talk, if you were there, we showed that even though RSA keys are not penguins, using AES ECB for key encryption is a bad idea, and even led to a key recovery attack on Mega. All in all, we presented 5 different attacks, which affected both file confidentiality and integrity, thereby completely violating the end-to-end security guarantees that Mega aimed for. And our conclusion was that securely implementing end-to-end encrypted cloud storage is actually not as easy as it might seem, and Mega faced quite a few challenges. So among these challenges are the fact that users tend to have multiple devices. And since end-to-end security relies on client-side encryption, this means that we need a secure way of transferring keys between devices in order to make files available everywhere. And this leads to a key distribution challenge. Furthermore, cloud storage systems tend to be browser-based, which means that cryptographically speaking, clients are assumed to be stateless. So for this reason, most cloud storage systems use passwords as a root of security. And as we know, passwords are not great for security. Finally, file sharing is an integral part of the functionality of a cloud storage scheme, but this means that there's user-to-user interaction, making the security setting inherently multi-user. So these things and more are what make securely implementing cloud storage tricky. And Mega actually didn't have a lot of help from us academic cryptographers in their attempt to overcome these challenges. But this was 2023, now it's 2025, and we'd like to give you an update on what happened since. So after analyzing Mega, Miro and I were curious about the general state of secure cloud storage. Now, Mega might be the largest provider of end-to-end encryption by default, but they're actually far from the only one. In fact, there's quite a selection of companies out there claiming to offer ultimate security and various other statements to the same effect. In particular, they really like to advertise something they call zero-knowledge encryption or privacy. Now, personally, Miro and I have no idea what zero-knowledge cloud storage means. So in order to try to figure this out and also see which of these very strong security claims that we can actually trust, we, and in particular our colleagues Jonas Hoffman and Kien Tuong Truong, went on to analyze these systems. And it turns out that most of them are actually insecure. And even the ones that aren't broken in practice have blockers that mean that they can't be provably secure. So what's the reason for this sad state of affairs? Well, we claimed back in 2023 that the challenges were key distribution, password-based security, and file sharing. And while this is still true, Mega and the other providers that we studied actually managed to overcome these hurdles, mostly. So we think that, we're probably preaching to the choir here, but we think that the larger problem faced by these providers is that they didn't really know where they were going. There had been no formalization of secure cloud storage, so the cryptographic goal wasn't entirely clear. And in particular, there was no formal model, so it was impossible to design a provably secure cloud storage system. So that's what we set out to change. In our paper that we presented at Crypto last year, we presented a security model for end-to-end encrypted cloud storage, including a syntax, game-based security notions, and a provably secure proof-of-concept construction. So this is also the outline for the rest of this talk. I will briefly touch upon syntax and then hand over to Miro for security notions and the construction. All right, so let's dive into our framework. Now, you might think that modeling end-to-end encrypted cloud storage should be trivial, because this is just file encryption, right? But actually, to capture the complexity of a cloud storage system, we need to model interactive protocols in a multi-party setting. And this starts to sound a lot like key exchange. Now, I know there's a lot of key exchange lovers out there in the audience, so congrats, today's your day, because end-to-end encrypted cloud storage turns out to be even more complex. And we won't even talk about zero-knowledge cloud storage. So what makes modeling cloud storage so complicated? Well, as I said, similar to in key exchange, we need to model interactive protocols between multiple parties. Now, in our setting, these parties are a client representing a cloud storage user and a server representing the cloud storage provider. However, in contrast to in key exchange, there's not just a single protocol running between these two parties. Rather, in our syntax, we capture the core functionality of a cloud storage system with 7 different interactive protocols. And this substantially adds to the complexity of the modeling. So let's take a look at what these protocols do. The first one is account registration, and this is used to register an account with the cloud storage provider, essentially creating a new user in our model. Once a user has an account, they can use the authenticate protocol to log into it and start a session. And a user can have multiple sessions running in parallel, for example, on different devices. Inside an active session, a user can use one of the following 5 protocols to then manage their files. So for example, put to upload a new file. Now, the main complexity of the syntax is that, similar to in key exchange, we wanted to model the fact that these operations are non-atomic in practice. So in particular, this means that our syntax is entirely message-based, and we allow interleaving of messages, both between different users, different clients, and different protocols running in parallel on the same client. Furthermore, as we said before, there's also user-to-user interaction through file sharing, which is captured in our model through the share and accept protocols. And as we also said before, one of the challenges of end-to-end encrypted cloud storage is implementing the secure channel that's needed to transfer key material between different users. Now, in practice, the channel can be instantiated in a multitude of different ways, for example, by relying on a public key infrastructure, using a secure messaging app, or through password or link sharing. But in our model, we chose to capture this through a generic, unidirectional out-of-band channel between the sender and the recipient. And this can both be seen as a simplification, which allows us to focus on the core cryptography of a cloud storage system, but it's also a way to make our model generic and ensure that we can capture all of the different ways in which this channel can be instantiated in practice. So with that, I'm going to hand over to Miro for security.
Our goal for modeling security is to capture the security against a malicious cloud provider. That means that the adversary plays the role of the cloud provider in the protocol, and it can specify all of the messages sent from the server to the clients. Moreover, the adversary also controls all of the operations executed by honest clients through oracles, one for every core functionality that Matilda introduced. So for example, the adversary can use the register oracle to make a client start a registration protocol run and send the first message to the server. The server can then, or the adversary can then reply to that message. And similar to key exchange, the adversary can also make the client execute the next step in that ongoing protocol run using the next oracle. Recall that security is password-based, which means that every user has a password which is sampled from a password distribution that parameterizes our game. And different users could even have the same password. These passwords are unknown to the adversary, but of course the adversary could guess a password, and this will show up as a password guessing advantage in our security proofs. Furthermore, the adversary can also compromise a user using the corrupt oracle and learn their local state as well as their password. And we model both selective and adaptive compromises. We formalize 2 basic security notions, integrity and confidentiality. For integrity, we model this with an int ptext style game, where the adversary wins if at any point in the interaction, it can inject or modify a file sent to the user without that the honest user would notice this. Note that this is not an int ctext style game, because we are using message-based syntax, and so we don't define when the ciphertext is actually sent to the user. In fact, the ciphertext could even be split across many different messages. The downside of this is that our security notions also cannot refer to ciphertexts. For confidentiality, the adversary wins if it can learn anything about the files that are uploaded except their length, or in addition to their length. And we model this with an int-CCA style game, where the adversary can use the challenge oracle to specify 2 files, which one of them is then encrypted and uploaded by an honest user. And the goal of the adversary is to guess which file was uploaded. Now recall that all of these interactions run while the adversary has full control over all of the other operations that honest clients concurrently perform. And so there's a lot of complexity in formally modeling this, and we need to exclude a lot of trivial attacks very carefully. All right, so let's recap. When we started working on end-to-end encrypted cloud storage, it was an elusive goal that hadn't been formalized in theory and therefore wasn't possible to achieve in practice. Now we've formalized the syntax of cloud storage and defined security notions, making this goal concrete. Namely, we defined confidentiality and integrity, and with these security notions, we can formally capture the attacks against Mega, showing that they fall short of achieving the goal. But we're still missing a construction, a cloud storage scheme that can make it to the goal. So the last thing that we'd like to talk about in this talk is our proof of concept protocol called CSS, which is a cloud storage scheme where we were able to prove that it achieves confidentiality and integrity, and so that makes it the first provably secure cloud storage scheme. So let's see how CSS works. CSS is a two-party protocol that is an interaction between a client and a server. The client takes as input the user password, as well as a globally unique account identifier. And then it runs an interactive protocol with the server to compute an OPRF on these password and account identifier values and derive a key. The server uses an OPRF key that was picked by the client at random during registration. This somewhat unusual choice is because we don't trust the server to honestly generate this key. The OPRF key is then used in a PRF to derive different keys for different purposes. First, the client finishes authentication by deriving a MAC key and then using that to compute a tag on a session identifier that is picked at random by the server. And the server can verify this tag using the same MAC key, which was previously exchanged with the server during registration. If this verification succeeds, the server considers the user authenticated and allows the user to perform file operations. From the OPRF key, we also derive a key encryption key. This key is used to bootstrap the file, the key hierarchy used to encrypt files. But we don't use this key directly to encrypt file keys. Instead, we encrypt a master key that's picked uniformly at random. And then we use that key to encrypt the fresh random file keys that are picked for every file that needs to be encrypted. The reason for doing this is that this allows the user to change their password without that we would have to re-encrypt all of the file keys. Now, the resulting file ciphertexts need to be uploaded to the cloud provider, but we also need to upload the encrypted file keys as well as the encrypted master keys, so that the user is able to recover all of the keys in the end and decrypt their files. All right, so let's conclude with looking at the history or development in cloud storage. Starting in 2022, there were various attacks on cloud storage providers, breaking Mega, Nextcloud, and others. And so we took a step back and formalized the goals that you want to achieve for end-to-end encrypted cloud storage. However, there's still a gap between theory and practice. And while our protocol CSS is an attempt to bridge this gap back to practice, we need your help to truly bring provable security for cloud storage to practice, and in particular to build a deployed protocol with provable security. So there are still a few things missing. CSS currently only exists on paper and doesn't have an implementation that's ready for a large-scale deployment. We're also very interested in hearing your feedback, ideas for model extensions, or crucial features of cloud storage that we missed. Also on the theory side, currently CSS only has a proof in the selective security model, and proving it adaptively secure is an open problem. Our full paper is on ePrint. Thank you very much for your attention.
We have time for one quick question.
Your construction, I guess, uses OPRF, and right now, even though there are a lot of advances in post-quantum OPRF, my understanding is it's still not super practical, even though I guess it's improving. So do you have any ideas or any modifications to your constructions that could be made post-quantum secure today and efficient?
We have not thought about this. This is a very interesting question. In our construction, we had to specifically use 2-hash Diffie-Hellman to make our proof go through because we relied on the hash functions modeling as them as random oracles. So I think this will be a deeper change to figure this out.
So it's not even generic, yes. I mean, it's a nice framework, but you're saying you instantiated non-generic.
The OPRF is the one thing that we had to not handle generically. The other building blocks are generic, yes.
In particular, the reason for this is that we're in this malicious server setting, and OPRFs aren't usually proven secure in that setting to begin with. So we don't only need a post-quantum one, we also need a post-quantum malicious server secure OPRF.
Thanks.
I think we'll have to cut off the questions now, and hopefully you can catch Matilda and Miro.
Please find us
during
on the hallway.
break. Thank you.